Good afternoon, everybody. So today we have the pleasure of listening to Sylvia Serfaty, who is a professor in Quant Institute in NYU, and this year she's invited on the chair of the Fondation des Sciences Mathématiques de Paris, and so she gives a course not every week, but almost every week in ENS. And so the first class was last Monday, and the next one is this Monday, right? Mean field limits and classes, right?
Yeah, so the course is more on Coulomb lessons. Today I talk more about mean field limits.
Okay, and so today Sylvia will talk about mean field limits for singular dynamics.
Okay, thank you very much. So it's a pleasure to be back here and to give a talk. Thanks for the invitation. So I want to discuss some older and more recent developments on this sort of modulated energy method for proving mean field limits for systems of particles with singular interactions. Okay, so what do I mean by that? Okay, so let's say you define an energy like this, the sum of pair interaction potentials. Donc, what kind of interactions do we want to look at? The model case, so 1 over x to the s, maybe some constant here. It's just useful to put the s here so that you can see formally the case of the logarithmic interaction as s going to 0 limit of that. So when I say s is 0, it's the logarithmic interaction, and otherwise it's a Riesz type interaction. And that includes Coulomb. And there is a constraint here, you see that s has to be strictly less than the dimension, because if you're above s equals d, then the interaction is not integrable near the origin. It's a completely different regime for the dynamics. Okay, so I will not talk about such a case. Okay, so what we want to look at is systems of the East that correspond to various possible evolutions. Mostly I will focus on these two. The gradient flow. So here you see it's in a mean field regime where each particle is feeling a force which is the average of the force exerted by the other particle. So you take the gradient with respect to the entry I of the energy. And of course you put a minus sign so that it's a descent. And you can also look at conservative flows, for instance, like this, where here you have a matrix J which is antisymmetric. And the physical evolution, Newton's law, where the acceleration is equal to the average force generated by the other particles. So this is really the physical law. If you have, for example, charged particles with Coulomb interaction. Okay, and in addition to that, if you want, you can add some noise term. So you take theta to be a temperature, square root of theta times the Brownian motion for each particle I. So there are, let's say, in the simplest case, n independent that are just added to your dynamics. So here is the plus. Okay, so what kind of questions do we want to understand? Of course, we want to understand the large n limit, an evolution like this. So let's look at it in a general form. Like that, here I look at first order evolution. So it's only a first derivative in time, and I have general interaction kernel K. And I added, you see the diffusion term. So you ask what is the limit of the empirical measure. So the empirical measure, you put the Dirac mass at each point, divide by n, that's the probability. You expect that it is going to have some weak limit in the sense of probability measures, mu t. And mu t is going to be solving some evolution equation, so some PDE. And so you want to prove this limit for each time as n goes to infinity. An alternative point of view is to think in terms of correlation functions or marginals of density functions. So here you give yourself some initial distribution of particles. This is some initial probability density Fn naught, probability of seeing your system at point x1, xn. And you ask what is Fnt, the same probability after you have evolved your points according to this dynamics. Okay, so there is a notion that's pretty famous, which is the propagation of chaos. You say that you have propagation of chaos if whenever the initial density is tensorized, or if you want in the probabilistic language, it's IID according to a low mu naught, then at later times your FNT is approximately factorized like that. And of course, you expect that the law mu t is the same as the one you would obtain from the convergence up here. So in fact, of course, this does not make sense because this is a law on RD to the power n, and n is growing. So you cannot really take the limit of that, but you can take the limit for k marginals, which is what you would obtain by integrating over all variables except the first k. You fix k, and you let n to. Okay, so it's a fairly standard fact that, in fact, these two points of view are kind of equivalent. So I don't want to go into too much details, but there's things like that. In particular, if you can prove convergence of the empirical measures, then you can deduce the convergence of the k-point marginals to the tensorized states. Okay, so I will mostly be focusing on this point of view. Okay, so what is the formal limit that we expect? So the first thing is you can do a sort of back of the envelope formal computation, and you use a fact which is a good exercise for teaching distributions in an undergraduate class. For instance, you ask them, prove that in the sense of distributions, if you have a Dirac mass at a point x which moves in time, so x of t, then you solve in the sense of distributions dt delta x of t plus divergence of x dot delta x of t equals 0. It's like the transport with velocity x dot. Okay, so if you sort of plug in the law you have for x dot here, you will get an equation like that. Another way of doing it is to use this formulation with this density function that I was mentioning before, and see that Fn that depends on time solves a big equation like that in Rdn. And then what you have to do is you have to write a hierarchy, because the problem is when you look at the marginals of your Fn, the equation for the first marginal involves the second marginal, because the interactions are pairwise. And then the equation for the second marginal involves the third marginal, etc. So you can have a hierarchy. But if you imagine formally that your thing is tensorized already, then you can guess what you get. Okay, so the equation, that's the limit, at least the formal guess, is that dt mu equals divergence. And so here you're going to have the effective velocity, which is the the mean field velocity is going to be just the convolution of k with the distribution, because you sum k of xj, you sum k of xi minus xj. With ai is fixed, but you sum over j. So when you do that, it's roughly k convolute multiplied by mu, because that's the density. And if you have a temperature, you get an extra Laplacian term in your equation due to the diffusion. So from the point of view of PDEs, having a temperature is kind of good, it gives you an elliptic term. If you happen to look at the second order dynamics, which was the xi dot dot equals the average force, then the right way is to think of it in kinetic formulation. So you have to write an equation not for the density mu in space, but for the density in space velocity. You write a rho, which is a density in position and velocity. The marginal of rho with respect to the first entry, the position, is mu. And then you have a Vlasov type equation, you see, where dt rho plus v dot grad rho, so that's the free transport along velocity v, plus the force, which is again convolution of gradient rho, and maybe also a diffusion term equals 0. Okay, so that's what you expect. So now you want to prove this rigorously. So you want to prove these convergences as n goes to infinity. So what are the ways to do that? So the classical methods, they actually work mostly when the interaction k is quite regular. Okay, so here I've taken a general form of interaction. So these methods, for example, one is this trajectorial method. You look at your solution of your ODE system, and then on the other hand, you look at the solution of particles, at the evolution of particles that follow the characteristics of your limiting equation, your limiting PDE. So they follow this sort of idealized motion, and you check that if they start at the same position, they remain close. And so that works well if K is Lipschitz. If it's not so regular, so remember we're interested in treating singular interactions, like inverse powers of the distance, then you have to work harder. So Auré-Jabin, for instance, have been successful in working with controlling how close the points can really get, so that they cannot get too close in some regimes, for some case. And then other methods have been developed that work at finding a good metric. And typically, they work with Wasserstein distances, so one Wasserstein or other Wassersteins, in which you can prove stability. So here, this is the kind of thing you want to prove, that the time derivative of the distance between two solutions, mu1 and mu2, grows at most like that distance itself. And then with Grunwald's lemma, of course, you show that if you're initially the same, it will remain the same. So this, in principle, this can prove you a uniqueness principle. But what you want is, you want a weak, strong uniqueness principle. So you want to be able to show something like this. When mu1 is a true solution to your limiting PDE, and mu2 is actually the solution to the discrete problem. So it's the empirical measure, right? So it's not going to be a strong solution. It should be, at best, a sort of weak solution. So if you can do that and you apply to these two measures, you have some chance. So you have some chance of proving convergence in this way. And then a third method that has been revived recently, by Jabin and Wang, is to use relative entropy. So that is a method that works when you have temperature diffusion, because relative entropy is well suited to these sort of probabilistic problems. And so here you look at, you define like this the relative entropy, and it's for the full density function, Fn, and it's relative to the expected guy, rho tensor n times. Again, it's just defined like that, normalize it properly. It has a sign, and it's also like a distance, right? It's not a distance, but it's almost like a distance. So what they managed to show is that if you differentiate this in time, you can control the derivative in time by the relative entropy itself. Of course, whenever you do that, you use the PDE for rho. So rho is not any rho, it's the rho that solves the limiting PDE. So you use the PDE for rho, you use the evolution for Fn, and you have to be quite lucky to manage to control all these terms by the relative entropy itself. So with that, they managed to do certain types of not so regular interactions, but essentially, I think the condition is that K is in W minus 1 infinity. So they are barely able to include the log interaction. So because they managed to write log as a, but not more singular than log. Okay, so now I'm going to specialize to the case that I was interested in, where the force derives from a potential. So here, instead of being a general K, it's a gradient G. And G is my singular interaction. So that's the equation rewritten in this. So MF, like mean field equation. And here I put a matrix M, just to be able to treat two cases at once. The case that's dissipative, the gradient flow, then it would be M equals identity. And the case that's conservative, the Hamiltonian type flows, where M would be an anti-symmetric matrix. Okay, so the only condition that you need, what you really need, is this MC dot C, non-negative. Okay, so these equations, there are PDEs. It happens that one class of them has a name. They're called the fractional porous medium equation. That's for the dissipative equation. When I take this particular Riesz interaction, G is 1 over XS. So there is a literature on such equations, and we are going to typically need some PDE results to make the proofs work. If you're in the system with the situation of the second order evolution, where you get a Vlasov equation, then this is the form of the equation, and if G happens to be the Coulomb interaction, then it's really Vlasov-Poisson. It's a well-known model for charged gases, plasma. So on these particular types of interactions, so the singular inverse power interactions or logarithmic interactions, here is a brief summary of what was known. So I should mention that the two-dimensional log case is particularly interesting because in fluid mechanics you encounter the point vortex system. So if J is exactly a rotation by pi over 2, right? And if you write dt mu, or if you write dt xi, rad log, right? You may recognize this as the point vortex system in fluid mechanics, and the limit is the Euler equation in vorticity form, you know, with the Biot-Savart's law. So the Biot-Savart is exactly saying you take the Bragg perp, so here you have Bragg perp of the log. Okay, so people have studied it for that reason. They proved convergence. They proved convergence in the case you noise, then it's Navier-Stokes in vorticity form. Then there were some results with the stability in Wasserstein spaces, as I mentioned, and some results that work for dimension 1. Okay, so here these results, they are kind of limited to sub-Coulombic cases. You see S is the power here, and Coulomb is exactly S equals D minus 2. Okay, so this was just below Coulomb. Now, the one-dimensional results, they're not limited like that, but in one dimension, you have a big advantage is that the interaction becomes convex, and that you lose as soon as you're in higher dimension. So the convexity can really help you. Okay, and then there was this modulated energy method that I'm going to present, which was first implemented by Mitya Durinx in his thesis on this type of model, and at the time it was only for low dimension and low S. Now, when it comes to the second order evolutions, same problem. You see here we're stuck at S less than Coulomb, so it doesn't allow to prove convergence of Lazare-Poisson. And there is this relative entropy method that yes, modifications. Okay, then some results when you cut off the kernel. Okay, so now let me describe this modulated energy method, which originally I had introduced in the context of deriving also mean field evolutions, but in Gibbs-Boulandot vortex dynamics, so not a discrete problem, but a PDE problem. So it was a PDE to a PDE, so sort of going from quantum fluids to classical fluids. But okay, so in this context, what is the idea? It's again the idea of using a good metric. Okay, so now except that the metric, it's not Wasserstein, it's a metric that is based on the interaction itself. So G is my interaction. I just form this double integral and consider that this is essentially the distance squared between mu and nu. So mu and nu are two probability measures of densities. Okay, so you look at this sort of total width interaction between your two distributions. You see now that it's better if it's actually important that S be strictly less than Z, otherwise this thing is never well defined. And you also see that you can write this in Fourier and see this as a negative Sobolev space, a negative Sobolev norm. So in fact, it's an H dot T minus S over 2. And so what you want to do is, again, try to prove a weak, strong uniqueness principle for the equation from this metric. So first, you better prove it for the limiting PDE if you want to be able to get somewhere. So you want to check that if you have two solutions to your limiting PDE, the one I called MF, like Michi, then they satisfy something like that after using Brownval. Or if you want, you can control the derivative in time of this by, and you have it. You have to ask that the constant that you control here depends only on one of the two solutions, not on the other one, or on the regularity of only one of the solutions. So here what we can prove is that this is true with a constant that depends on the L infinity norm of second derivatives of this G convolution. So I will come back on that. Okay, so if you can do that, then you're sort of in business, because then you can try to plug in the empirical measure and apply the weak strong uniqueness to obtain convergence. The only problem is that this metric does not accept empirical measures, because if you put a Dirac here and a Dirac here, at 0, G of 0 is infinity. Okay, so you have to modify it, and basically you renormalize it, right, by removing the diagonal. So here, instead of integrating over RD cross RD, I'm going to do the same with the empirical measure, minus mu, empirical measure minus mu, and remove the diagonal So this triangle here is a diagonal. So with that, in principle, I have removed the sort of self-interaction of the particles. Now this is defined, this is well defined, but it's less clear that it's going to work because you've changed the thing. So first of all, it's not even clear that this is a metric anymore. And it's not clear that this removal of the diagonal is not going to create problems in the two. However, the bottom line is that it works. So this thing, I call the modulated energy, because you see, it's like an energy, like initially we started from an energy that looks very much like this, but now you're gonna here insert mu, that's mu t, the solution to your limiting PDE. Okay, so it's going to evolve in time. So that's going to sort of modulate it. And so, in fact, this terminology is borrowed from previous modulated entropy methods or modulated energy methods that were used for proving limits like that. Okay, so this is the quantity Fn, Xn, U. So Xn here denotes my whole configuration, X1, Xn. Okay, the points X1 to Xn, and here you have the empirical measure. No questions so far? Okay, so now I'll show you why this thing is actually a good quantity. So I told you that formally it's like a negative Sobolev norm, but now because of this removal of the diagonal, it doesn't really have a sign, for instance. It's not necessarily positive. And so how to remedy this? The idea is to use a truncation method. So you want to replace the Diracs by smeared Diracs. So you introduce some parameter eta, which is a small length scale, and the Dirac by what is delta xi eta. Specifically, it's a measure on a sphere of radius eta. Because we have a sphere centered at a point, radius eta. You put a uniform density on it, or maybe not uniform, but something that's on the sphere. And thanks to that, you'll be able to put back the diagonal because the smeared Diracs now can be fed into the energy. So you have to put it back but remove it. So that's a sort of renormalization method. And the point that's important and that's less trivial, I would say, is that there is a monotonicity property. So it's not an exact, but an almost monotonicity property with respect to this truncation parameter. So when you grow the balls, when you grow your spheres, in principle, you change the interaction. So the interaction between points, the interactions between spheres is not the same. As soon as the spheres intersect, it changes the interaction, but it changes it by decreasing it. So it's monotone. It's not going to increase the interactions, it can only decrease it. So that's one point which is important. And the other point that's important is the idea of not using eta that are the same for all the points, but possibly letting eta depend on the point. So you can choose your truncation in such a way that you're not going to intersect the other spheres. For instance, you can take a truncation that's related to the minimal nearest distance to other points. Okay, and thanks to that, you see that your Fn is not bounded below, but it's almost bounded below because it's bounded by some positive quantity, which is the h dot norm of the smeared guys, minus an error, which you can show is, this one doesn't have a sign, but it's negligible. Goes to 0. So it's almost positive and it's almost a norm. So if you can show that this thing is small, in the end it will show you that this thing is small. And because the eta you can take quite small, it will also show you your empirical measures. Okay, so that's the idea. But of course, this truncation thing that I'm doing, it's hidden only in the proof. You don't see it in the result. Like there is no truncation. This is only a sort of technical side thing. So with that method, you can really close your Grandval argument, and this allows to prove that for S in this regime between D minus 2 and D, so I told you less than D, you always have to do that. And this is exactly super Coulombic. But then this method works, and it gives you that if you have a limiting PDE, the solution is nice enough. So here it has to be bounded in some interval of time and uniformly in space. And this guy has to be also bounded. You remember I showed you this quantity before. So G convolved with mu. I will call this H mu. That's really the potential generated by mu. Right? So if you think in terms of electrostatics, this is your like your Coulomb or Riesz kernel, and when you make the convolution, you get the potential. So you want that this potential has two derivatives that are bounded. That's in the Coulomb case, and there's a bit more regularity conditions that I'm not spelling out in the other cases. And then what you can show is that this modulated energy at time t is controlled by the modulated at time energy at time 0 plus something very small times an exponential in time, which has a constant C2 that depends only on the norms that you control. And so in particular, if you know that your empirical measures initially converge and the initial modulated energy is small, then you have that for this interval of time, 0t, you have convergence of the modulated energy. Hence, you have convergence of the empirical measures, because I tried to show you in the previous slide that this thing does metrize with convergence. Okay, so that answers the question for fixed intervals of time, and then you have to do a PDE study, right, to see if your limiting PDEs they satisfy this good propagation of regularity, if they have solutions that are bounded, if when the solution is initially in L infinity, it remains in L infinity, etc. So for most of these cases, actually, it's okay. And usually it's even in infinite time, global in time existence. Okay, so after that, Matt Rosenzweig improved the result. In particular, he worked on getting rid of these regularity assumptions. So you remember there was some assumptions here on the potential. He got rid of that in the logarithmic case. You only need to assume that mu0 is at L infinity, and if you're in this, so this is the, I should have written it's the 2D Coulomb case. And now if you look at D bigger than 3, it also works, but only for short times. And I think now he's able to show, basically you only need to assume that mu is in some LP space. You can work with critical spaces in terms of the code for the scalings of the dynamics. And this is all by modification argument. Okay, so you can get rid of some of the assumptions like that. Now we also have a shock rate. So I told you there is an error term here, which is small. I can tell you exactly how small it is. It's n to the 1 minus s over d, which happens to be a negative number. No, so it's s over d minus 1. Because I think it should be this, because s is strictly bigger than, strictly smaller than. And we can, there's reasons why this is short. You cannot make your modulated energy smaller than this order. Okay, with Mitya-Durand, we have shown that this method can be applied to get convergence of the second order evolution, so where you put xi dot dot here, to the Vlasov-Poisson equation, but when you're in a particular case, which is called the monokinetic case, the case when at each position in space, there is a unique velocity. There is a Dirac in velocity. And then the limiting equation is not quite Vlasov-Poisson, it's pressureless Euler-Poisson equation, so where you have a Dirac. So the non-monokinetic case, which is the real question, is still open. But here it works for Coulomb or even these super Coulomb interactions. Okay, so then after that with two collaborators, so still Matt Rosenzweig and Hung, and we revisited this proof and we realized that okay, you can make a modulated energy proof with almost the same modulated energy. And you can make it work for the other regime, which is S less than Z minus 2. Okay, there are other proofs for S less than Z minus 2. I told you before, you could go up to S less than Z minus 2, but not with the modulated energy method. So you can actually now cover all the range from 0 to D. And the other thing that you can do is you can say, why does it have to be exactly this? Can I relax this a little bit? Like, can I be Reese-like? And we can do that. In particular, what we need basically is we need assumptions on the Fourier transform. So the Fourier transform of this thing is very specific. It's an inverse power. Right? Well, it suffices to assume that your Fourier transform is bounded above and below by something of that order, and that your thing is bounded above and below by things of that order. So you can relax a little things, and thanks to that, in particular, you can now include things like Leonard-Jones type potentials, so meaning things that will have a behavior near zero, a singular behavior near zero, and near infinity that are not the same. Because after all, that's nice. Okay. I want to say a bit about the case with noise. So when you have noise, you can try to look at the expectation of the modulated energy and see if you can control the derivative of that in time, and again have a ground value argument. And that works only when S is less than D minus 2, so what I call sub-Coulomb. Okay, so that has worked and we've done it. Okay, now what about super Coulomb? So for super Coulomb, in fact, there's some difficulties when you differentiate that in time. You get some bad terms that you don't know how to control. But Bress, Jacques-Louis, and Wang realized that what you should do is you should combine the relative entropy method that they had used before and the modulated energy method and put them together into something that is a modulated free energy. So what is that? So it has two terms. So you remember now this density probability of density little fn. So now the modulated free energy of Fn relative to rho is the relative entropy that we have seen before, Hn of Fn relative to rho tensor n times, multiplied by the temperature, plus the average modulated energy, so the integral of the modulated energy against the density Fn. So when you do that, you really mimic a free energy in physics, because a free energy in physics is something that's like an energy plus temperature times an energy. And now when you differentiate this thing in time, the time derivative of the modulated energy, I told you they show what shows up, there are some bad terms that are very singular. In fact, I can tell you what they look like. They look like that. Because of Ito's formula, you have Brownian motions, you have to apply Ito's formula. When you apply Ito's formula, you get Laplacians. And you don't know what to do with that, except that when you differentiate in time the relative entropy, you also get bad terms, and I think they have also been stuck because of these bad terms. We got stuck with bad terms, but if you put the two together in the right way, they cancel. So the bad terms from this side are exactly equal to the bad terms from that side if you put the right constant in. So now that works, and you can apply the same method. The only difference is that this thing works only for dissipative cases. So you cannot do Bragg curve. You cannot do the point vortex system. You have to have a gradient flow. Whereas the first item here, that works for dissipative or conservative. Okay. So with this method, they were able to treat also all these risk cases that we mentioned up to D, generalizations of risk cases as well. And also some attractive logarithmic interaction. So if you have an interaction which is attractive logarithmic, means you change the sign here. So instead of minus log, it becomes plus log. It's attractive, but because you add some noise, the evolution is not, not singular. So it can run for a bit of time if the temperature is large enough. And the mean field limit is expected to be the Batlag-Keller-Segal equation in the subcritical case. And thanks to this modulated free energy method, they proved this convergence. It's a very nice result. Answering an open question. Okay, so now I rewrote essentially what I just said. If you have initial density, Fn0, Fnt solve your ABUV equation in this big space. Then, if you have a regular enough solution to your limiting thing, you can show the control of the modulated free energy, and you can deduce the weak convergence sense of marginal. Okay. So now I want to show you maybe a little bit of the key points in the proofs. The first key point was you introduce this modulated energy. Okay. The second key point is when you differentiate it in time, these are the terms you get. Okay, so what happens? You take sum of g xi minus xj, and you differentiate in time. So you get derivatives of xi minus xj, and they hit the gradient of g. So now this is exactly what you're going to get. You're going to have derivatives of gradient of g, and these are the derivatives of your points. So there's some vector field here, which is related to the dynamics. So it's going to be, for example, this in the evolution I looked at. it doesn't matter really very much what it is. But you get expressions like that, and now the question is, can you control that by the modulated energy itself? Okay, so what you want is really a functional inequality. So you forget where this thing came from, you forget that it came from a dynamic problem, and then you ask purely, if you want, a functional analytic question, also a sort of harmonic analysis question. Is it true that if I look at an expression of this form, I can bound it by the modulated energy plus a small error? Okay, so well, the answer is that it's true. And now we call that a commutator estimate. And why commutator? Because if you look at what this is doing, it's doing, so if you write F to be this distribution, which is the difference between your empirical measure and a reference measure mu. So here again, you forget that there is some dynamics associated with that. Just some reference. What you're doing is psi dot G convol with F minus G convol with grad, actually a divergence of psi F. So you see that you're commuting two operations. If you want to write it precisely. Okay, so when you commute two operations, you sort of hope that there's going to be a little gain in derivatives that you can recuperate. And in fact, people have been looking at things like that in singular integrals, using things that are complicated, like these Journet operators. But we could not use any of their results because they all assume that the divergence of psi is 0, which is not necessarily the case. And it's quite complicated what they do. They use power product estimate. So we have a simpler proof. So this estimate, as I said, is the key. So it's been reused to do other things with the quantum Coulomb infinite limit, quasi-neutral limit. Once you have that, so I'm going to show you how you can write a short proof, but in the Coulomb case for simplicity, for the permutation. So remember we defined potentials. HF is the potential generated by F. So if you're in the Coulomb case, it happens that the potentials of Poisson's equation minus Laplacian H equals F up to a multiplicative constant, which is called CD. And so now the modulated energy, formally, it's the same as this double integral. So we're going to rewrite it in sort of electrostatic terms. So I don't, this is called carré du champ. So this is the potential H integrated against F. And so that's the same as H integrated against its Laplacian because of this, with a minus sign in front. And now you integrate by parts, you apply Green's theorem, you get the square of the gradient of the potential, you get the Dirichlet energy. So there are some boundary terms in principle, but you assume that F integrates to 0. This way your boundary terms at infinity are actually cancelling. Okay, so now it's good to introduce something that is well known in calculus of variation and mechanics, which is called the stress tensor. And so the stress energy tensor I write it like that, for grad H, it has two indices ij, and you define it like this. Then you compute that, at least formally, the divergence of the stress tensor is exactly 2 times the Laplacian of H times the gradient of H. That's going to be true if everything is regular enough. So it gives a meaning to grad H times, so it's the same as giving a meaning in the sense of derivative of F. Okay, so whenever I see this expression, I can rewrite it as the divergence of something that happens to be the stress tensor. And you see the stress tensor is a bit like the energy. It's in the same space as the energy because of this computation. Okay, so now you have a one-page proof in this simplified setting. I just copied what I said. So whenever you encounter things like that, by the way, formally, you see that this looks like it could be like the energy because you take a gradient of G. So G is an inverse power, so 1 over x to the s, right? But when you get a gradient, you get an extra power, so 1 over x, s plus 1. But here, if C is Lipschitz, you regain an x minus y. So 1 over x, s plus 1, minus 1, so 1 over x, s. So formally, P of this is like G. But F doesn't have a sign, so you can't really make a proof of that. But it's plausible. It's plausible. Okay, so now if you rewrite this, you have to desymmetrize the expression and see that it's 2 times psi of x, and then you recognize the potential because you have a gradient of G convolved with F, so I'm going a bit fast. you recognize exactly the type of expression that we learned how to control, F times gradient of H. Okay, so now you can substitute the divergence of the stress tensor, and now you're happy because you can integrate by parts, and you can put the derivatives on psi, and you see that if psi is Lipschitz, you control this, and because the stress tensor is pointwise controlled by grad H squared, you control exactly by the energy. So this is using my first carré du champ. Okay, so this is the functional inequality in the Coulomb case, except that this is cheating because I looked at the case where you don't have Diracs. Because if you have Diracs, you cannot do the double integrals, you have to remove the diagonal. So that's the difficult part, is to renormalize this inequality. To make it work when I remove the diagonals on both sides. And that's where I use this truncation smearing procedure of the field that I described. So this works for Coulomb. Eventually, it also works for Reed bigger than S, for S bigger than T minus 2, but eventually we also worked with Hang Nguyen and Matt Rosenzweig, getting rid of that proof, because this stress tensor proof really locks us into this exact inverse power. So if you want to do things that are not exactly inverse powers, we cannot use this stress energy tensor method. And so we got rid of it and we found a proof that's in pure space, nothing crazy, no power products, not even Fourier transform. It's fairly, it's understandable by me, for instance. So this functional inequality, it has an existence beyond this sort of one-dimensional manifold. Okay, so now I want to finish by talking about another question that's natural once you've done that, which is, can you get global in time convergence? Because all the convergences that I showed you, they are exponential in time due to the use of Grunwald's lemma. And so in principle, in long time, you could lose convergence, or you could get far away from your limiting equations. So what can you do to get global in time convergence? So there was one approach that was followed by Guillain, Lebris, Salmon-Marché, is to go back to the Jabin-Wang relative entropy method and say, okay, if you look at the Jabin-Wang proof, you differentiate in time the relative entropy. When you differentiate the relative entropy, you get a negative term, the dissipation of entropy, which is a Fisher information. Okay, so you get a negative grad F squared. Now, if you can try the time derivative, the other part of your time derivative, you can try to absorb it by that negative term, thanks to a good functional inequality. So what functional inequality do you need? Some kind of logarithmic Sobolev inequality. And so they managed to prove that, and thanks to that, you can show that the entropy dissipation is controlled by the relative entropy itself, and you can get actually exponentially decaying convergence rate. So that they managed to make it work in the Jabin-Wang setup. That was the setup where you only use relative entropy. And I told you, you look at forces that are like that. This is their setup. Okay, so something we did with Matt Rosenzweig is to say, we can also do something which is to take advantage of the decay of the limiting solution if we know it. Okay, so if our limiting solution has not really a mu t that decays, but the gradients of mu t that define the limiting velocity fields. The limiting velocity fields basically decay in time. We can try to put that into the Grunwald and get uniform convergence. So we first did it in the soft Coulomb case with this modulated energy map. And so the work, really the work was this PDE work, which is to show that mu t has a good decay. Now remember, this is a case where we have noise, so we have a Laplacian in the equation. Right? dt mu equals divergence of blah blah blah, convolution. But we have the Laplacian. Okay, so what we hope is that in the end, it's the heat equation behavior that dominates. So you can take advantage of the decay given by the heat kernel, and we prove this type of result that mu t, the norms of mu t are going to decay like. So this is a negative power, so it's going to decay like an inverse power of time. So this was inspired by some results by Carlin and Ross on equations that look like that, but they were looking at divergence-free transports. Okay, and so now what we do is we go back to this this functional inequality, the commutator estimate functional inequality that I showed you before, That inequality, if you pay attention and you look at how it depends really on this side t, so now this is going to be my velocity field, you see that the factor that's in front is bounded by the L infinity norm of your solution to some power. Okay, so this is in all space, right? So you start with the distribution of particles, and then the particles repel each other. Right? You have some diffusion, and you have the repulsion. So eventually, the whole thing just collapses to zero. It's going to zero, like 1 over t to some power. So this thing is going to zero. If you put that in the ground valve, if the rate here is integrable in time, you will get a uniform rate. Okay, because in Grunwald's lemma, you integrate the function in time. So you don't have to have an exponential, you can have an integral of a convergent function. And so thanks to that, we get, so this is your theorem, so it works only for dimension bigger than 3, because otherwise we don't have a good enough decay. And it was for this sub-Coulombic situation, and now we were able to get a convergence that's uniform in time. And in the other case, when S is bigger than d minus 2, I told you in that case, you don't want to use the modulated energy, you want to use instead the modulated free energy of Brezhnev-1. So we worked in the case of the torus because the torus is better, in particular for you keep a lower bound on the density. Right? So whereas when everything spreads, you lose a bound on the density, and that's quite delicate. But so in the torus for S bigger than d minus 2, we did the PDE study. It's the main work here is in the PDE study to prove the exponential decay. So this time it's not algebraic, it's exponential decay of all the derivatives of the limiting solution. So it means your solution is going to converge to a uniform solution, but exponentially fast in time. And thanks to that, you also get a uniform in time convergence, and now you have it with this sharp, this optimal error term that I mentioned before. And in the case that Brezhnev had studied, where you have attractive log and convergence to Patla-Keller-Siegel, we can show that actually a uniform in time convergence is not always true. So above a certain, below a certain temperature, it will fail. So that's maybe a bit more support. Okay, so I stop here.
Maybe we start with questions in the room.
You get back to the slide in which you're defining inequality, in which you said that you have the estimate when the two measures are regular.
This one?
I think it's this one. So just to be sure to understand, you say that you cannot use directly this estimate when, say, mu1 is the empirical measure because it is too singular. And my question is, why can't you try to use it on the so-called smeared or convoluted measure? Because if you plug in the convoluted measure inside of it, then you have an equation which is modified with some commutator, I guess, or something like this. And this cannot be handled. This is why you have to define another energy.
Yes, I don't think it's good to do it this way, because if you look at the modified measure and then you look at the evolution of that, you're changing the evolution. And to deal with the change in evolution, I was not able to do that. To control the error that you make on the trajectories of your particles. You really change how you evolve the particles if you.
Yes. But I'm speaking at the PDE level. When you take the convolution, you know that if you have some kind of.
But you need regularity of your solution, right? It's the C0 1/3 typically. It's the kind of thing that you can use. But not on the discrete level. Right? It's like if you control at the level of your PDE, yes, it's okay, but at the discrete level, I don't know how to control that I'm not completely changing the evolution by doing that. So it's better to actually keep the evolution and change the definition. And so you do your smearing, but you hide to do it. You don't tell anyone. You come back. It's a different approach.
So this general argument, do you need theta to be non-zero? Is that necessary? Because I think
theta, no theta. In this theorem, there is no theta. This theorem has no theta.
Okay. So for the fractional porous medium equation, I think Vasquez and Caffarelli, so they didn't prove uniqueness. So have you established uniqueness for that?
So we have, yes, this, as a byproduct, you must have uniqueness for the limiting equation, otherwise the proof would be wrong. But it's uniqueness within a class of things that are initially quite regular. So yes, I think even in some cases it's a new uniqueness result. So you can use that method to prove uniqueness if you want. But sometimes, very often it was known by, but with regularity, one of the solutions has to be.
Other questions? Actually, I have one. So as you mentioned, you always have in most statements you have an infinity assumption on mu or maybe an LP. But I guess in some cases you can also be interested in the case when mu is just a probability measure. No?
Yeah, yes.
Something that doesn't even have a density with respect to Lebesgue. What happens in that case? Are there still some parts of the proof that can be salvaged, or do you think?
No, I mean, I think that math has probably done the best you can do in terms of relaxing the regularity on mu by modifying and stuff. But
or do you have counterexamples, things that don't work out well in that case?
For instance, if mu is not regular, you have examples of non-uniqueness.
Okay.
So you expect non-uniqueness. For example, you imagine your points could concentrate on a line. Right? So you could have an initial data with point concentration concentrated on a line in R2, and you guess that there's going to be non-uniqueness of solutions. So this proof cannot work. Yeah. So I think that in that case you have to prove, you have to use a different method, convergence to a non-unique limit. So it's not going to be a weak strong uniqueness. So, but I think it's because there is a real difficulty. It's not always. I'm a bit working on it.
Are there questions from the online audience? Oh, well, if not, let's thank Sylvia again.